So we're here to solve this Fillomino symmetry puzzle by Murat. As in other symmetry puzzles, it will be critical to just identify that center of rotational symmetry. With an odd region, the center has to be a specific cell. With an even region, it could sometimes be a cell, although that's uncommon. It's most often a border, but even sometimes a corner of the grid is possible. One place to start in this puzzle is in this upper right group. We have a 3x3 cell region, which will include an 8 polyomino within it that has a center of symmetry here. When an even group actually has a center of symmetry that's a cell, it can't use that cell. If you use that single cell, it can't have an even parity. So what that actually means is this puzzle starts by writing this quite uncommon Fillomino shape of a donut with a hole in the middle. It's pretty quick to start falling through down on this rightmost column, so that's what we'll do. See that once we get 3 6 cells marked, we get sort of the center of symmetry of that region, and we finish out this polyomino. Similarly, the 4, we get that center of symmetry and finish it out. The 8 will extend out a bit. It actually can come one of 3 ways here, and this will be, the center of symmetry will be the edge, whichever next cell it takes, but there's nothing at the moment to tell us which is required. It's important, as in typical Fillomino puzzles, to recognize when we're just off a 1, it's going to have to take the value of a Fillomino shape nearby. It can't be another 1. Get to here. This is a good time to consider the options for a shape like the 4. A 4 can make a 2x2 square, or it can make an S tetromino, or in other circumstances can be a 1x4 shape for its symmetry. Those are the 3 fundamental shapes a 4 can be. Notice that the 2 options we have here, the 2x2 square and the S tetromino, use this cell. Marking that that cell is used helps us because we see that this 11 is going to have to escape through the channel like so. And now let's actually try to identify its center of symmetry. It has 3. It will need at least a 4th, potentially 5th cell to get to here. It could actually take both of these, and then this would be the center. But if that's the center, that will cause issues here. So the only possible cell that's the center, based on what we marked, is this one that I've just circled. Looking from what I've circled to all the other 11s we know, we mark these additional numbers into the grid. That will help us see that we're isolating really something like this 4x4 space in the corner, which will contain a 12 polyomino and something else in the center, but this 12 will be using the whole space, and the center symmetry is certainly the center for the whole region group, since we've hit the bottom edge and then on each of these sides of the square. What you'll see when you actually reflect the digits that you already know is we form another donut shape. This actually has 12 cells marked. We have 4 cells left in the middle here. It can't be a 1 with a 3 because the 3 would be a bent shape, and that's impossible in this variation. It can't be a 2 with a 2 because that's touching the same sizes. So we do indeed have a unique assignment like this. Marking this cell as a 12 limits the options for the 11 group, and we can now finish it out like this. One obvious cell off of this 3 that we can put in. We can do a little more up here up top. We notice that the 4 is going to be this S shape or that S shape, but we can't do further than that now. I guess you can see that whichever of these shapes it is, it's going to leave a lot of room that the 11 is going to need to use. That will sort of block off this side from the 6. This 6 now has to come down. Once it's coming down, the 4 actually only has one option left for it, which is this top one. The 6 could come down or come to the right. The center of symmetry will be the next cell, sort of the edge of the next cell it passes over. If it went this way, it would isolate that 2. So this is the way it goes. This 2, if it comes down, leaves 2 cells behind. That's not going to be something we can allocate without having the same shape touching itself. This 3, if it comes up, leaves another 2 behind. That would cause an issue. So this has to come to the left. We're actually starting to build a hidden polyomino shape in this space. This cell might be part of it, we don't know for sure, but even if this connects to the cell, it's now 2 in size, 3 in size, 4 in size. Again, we're not sure on this one, but it's touching polyominoes of a lot of equivalent shapes here, so whatever it does, it needs to take at least one more cell. It's going to need to keep doing this because we're needing to get to a rotationally symmetric shape, and we're not looking anywhere like it yet. Finally, by the time we're here, we're potentially seeing a rotationally symmetric shape that uses this as its center of symmetry or some other future cell, but until we're sort of through here, this is just a growing hidden polyomino. We'll help resolve it by closing out the knowledge we know on this 11 up top. This is its center of symmetry, just looking at how it's growing, and the 6th cell that's in the connected chain. So coming back to this shape, while it can still grow much larger, the shortest thing it can be is to use this center and come this way. So we'll mark it to here. Let's look back at this 8. It used to have 3 options for where it went. The 3 at the top is blocked off. One of those, the center of symmetry option on the left, would actually carry this 8 into an existing polyomino. So this is the center of symmetry. Forms this group size. We now have to figure out this polyomino can't take this cell because it's not symmetrically available there, but right now it's 8 in size and it's now touching an 8. So you actually get a cool discovery of a 10 cell hidden polyomino in the center of the grid. Finishing out what we know over here. Can mark these cells like so. The 4 is going to need to take this central cell, and it will be a 1x4 shape, however that fills in. We actually have, I guess, finally the opportunity to start in this corner, and you can actually, while we started in the upper right, the upper left is just as good a place to start, maybe a little trickier to start, but it has similarly a 3x3 region, which will have a large polyomino in it, just as the 8 was going to use this as its center of symmetry. The 7 does as well. Since the 7's an odd region size, the 7's central cell is part of that shape. It looks like this. Exactly 2 cells will be unused by that region. They're sort of the ones I'm touching. They'll be symmetrically opposite. The one clue that's down here doesn't want to have an empty cell right next to it, which would form another 1 polyomino. So if we were starting in this corner of the grid, the only information we can actually mark at the beginning is these 5 cells. We don't know which other 2 cells it will take. But the next place to look after marking this is that these 4s can't come together. That's not a symmetric shape, so this 4 has to come down. They can't continue coming down or it'll connect to these and form too large a shape. It can't form this S tetromino because that's going to touch to this group. So the only symmetric shape the 4 has open to it is this shape coming to the right. This 4 region also needs to get to a point of symmetry, and recognizing that it can't use all of these cells, it actually has 4 choices. It can be this S, it can be this 2x2 box, or it can be this S. All of them use this cell, and marking that cell is really helpful. If we didn't have this other progress on the right side of the grid, we could use that to get how these 6s work. We actually use the right side of the grid to get all the shapes, so you'll see that there are other ways to get this deduction here, but I just wanted to sort of confirm that there's solid footing to start in that corner. What we can do, since we have a 1 next to the cell, we know we need to use it. It actually forms this region shape. We get the start of this. 3 cells have been used in a 7, so the next cell it takes will be its center of symmetry. If it uses this cell, it collides, so this is the center of symmetry of the 7 region. It does this. We've taken 6 cells from the 12, so the next cell it takes will be its center of symmetry. If it takes this one, it's going to collide with a given clue, so this is the center of symmetry. You can write all of this progress in. And once you get used to seeing these centers of symmetry, you actually can get very fast in writing the results into the grid. This is maybe one of the trickier steps towards the end, and it's to consider that this 5 has apparently two options left to it. It can form an X pentomino shape like this, or it can come down and form an I shape. But in the I shape, a 5 is next to a 5, which is going to isolate this cell, which is itself next to a 1. Notice that I shape is quickly impossible because of the hidden cell there causing an issue. So if we actually mark this in, we start to really limit the choices around these spots. This 4 is actually the most limited and most critical. It has two potential options like so, but notice in this top one, it's going to leave a cell that can't be a 1. It can't also be a 2 and can't go further, so this top option is no good. And in order to fill this space, it has to come down. That gives us actually very quickly these 3s. This is a hard shape to fill, but it's a 2, 2 with a 1. This is a 2 coming up, which says that the cell is not used. And we just fill this out to get things complete. Now we have a 7 polyomino that's going to be in this. It's going to use cells within the shape. Again, its center of symmetry has to be a single cell, and the only cell that can be is this one. With this cell not used, with this cell coming off the border, the only functional form it has is actually that shape. The 5 has to use the cell here next to the 1. That's now its center of symmetry. So it will be like this. The 6, whatever it does comes across, and once it connects like this, you'll see it has to be a 1/6 size. The 9 is now easy to define like this. The 5 is just filling it in. 2 like so, 1 like this. This 3 cells could be 1 with 2, except for the 2 nearby, which makes it have to be a 3 polyomino. This is maybe the last tricky little spot to do, but it's really recognizing if the 2 comes down, there's no identity that these cells can take, so it has to come up, and we divide it like this. And that's the end of this puzzle. I think if you really are good at spotting centers of symmetry and thinking through the symmetric shapes and options, you can use either of these corners to break in. There's a little bit about the specific shapes and options where, for instance, all of the available choices for the 4 here use this cell. That would actually help you get how these, the 4 and the 6 work together. You're seeing how the center of symmetry of the 8 being a single cell made it have to use a donut shape, things of this sort. And I think the neatest part of the puzzle, besides probably these 2 donut holes, was this hidden 10 that pops out in the middle of the solve. So it, maybe some different experiences for a Fillomino puzzle here. Certainly a fun challenge for Murat. Hope you learned something, and we'll see you again soon.